So like I said, we are part of the way through lesson 11, and we are continuing now. So everybody who's not paying attention to this should maybe put your phones away, put your other stuff away. We need to talk about your adrenal glands. Now, they're named very appropriately. They're called your adrenal glands because they are adjacent to your kidneys, and maybe you'll remember from Bio30 that renal is the descriptor or adjective that goes with kidneys. Like you have renal arteries, renal vein, and so these are your adrenal glands. They're right next to your kidneys.
Which lesson is this?
11. You're part of the way through. Now you have two adrenal glands located on the tops of your kidneys. Each of the glands is made up of two parts. So you can see in my picture here, we've done a little cross section of it. The inner portion or inner layer is called your adrenal medulla. Anytime I say the word medulla, I think of the movie The Waterboy where Adam Sandler yells at the professor, maybe you have a problem with your medulla oblongata, and then I giggle a little bit because they're talking about an alligator. It's funny. So there's the adrenal medulla, the inner layer. And then there's the outer layer, which is called the adrenal cortex, and we've used the word cortex before. It is the outer layer of your brain, the outer layer of the cerebrum. So the word cortex is continuously meaning the outer layer of something. You've probably seen the word medulla in several contexts. Of course, it was one of the structures in the brain. But when you talked about your kidneys in Bio20, actually it kind of depends on when you took Bio20, but maybe you learned that there are three layers there as well. The renal cortex, the medulla, and the medulla is always like the inner or middle layer. And each of these portions of your adrenal glands produce different hormones. And the reason they do this is because they're sort of hooked up to different aspects of your response to stress. So before we get into the details, I wanted to summarize this. When you react to stress, you have sort of a twofold response to it. You have an endocrine or hormonal response, but you also have a nervous system response. And so you'll recall kind of at the beginning of this chapter, I said sometimes it's hard to distinguish your nervous system from your endocrine system effects because they work together in so many processes, and this is a really good example of one. Here are some things that we could compare. For example, mode of action. Well, endocrine systems work by putting chemicals into the blood. That was kind of like the definition of what made something an endocrine gland. It's secreting a chemical messenger into the blood that we call a hormone. Your nervous system works using neurons that we studied in chapter 11. The endocrine system, like I said, was a hormone. Your nervous system works on nerve impulses. So action potentials. We learned all about those before. How action potentials are based on the membrane being depolarized, sodium rushing in, potassium rushing out. Between two neurons, there's a synapse where neurotransmitters are produced. The other two are something maybe that's new information. Your endocrine response to stress is a slow-acting effect. It's not immediate. You're not going to notice the response of your endocrine system within milliseconds. But your nervous system response to stress is fairly immediate. We learned about your sympathetic nervous system and how when there is real or physical danger or stress, the symptoms that happen are almost immediate. Your heart will race, your mouth will become dry, things like that. On the flip side, the duration of the effect for your endocrine system's response to stress is fairly long. It's not like after having secreted a bunch of hormones into the blood, the effect will just end a few seconds later. Whereas with your nervous system, once the impulse stops happening, then we stop having the effect. So the endocrine system is slow to get going, but the effects last longer. The nervous system gets going really quick, but the effects don't tend to last as long. Now, if we consider short-term stress first. Short-term stress is stress that doesn't last a super long time. Short-term stress is carried out by your adrenal medulla. That's the middle portion. And here's how it works. It's making a couple of hormones. Epinephrine, otherwise known as adrenaline, and norepinephrine, otherwise, I should have written noradrenaline there. That's funny. It's called norepinephrine. Now, epinephrine and norepinephrine aren't the same, but the difference between them is sort of a more biochemical thing that's beyond the scope of our course. They act on different receptors. And so they get kind of grouped together here. They regulate the short-term response to stress. The short-term response to stress is part of your fight or flight response. So if you think of the sympathetic nervous system, that's what's happening here. Sympathetic neurons carry a signal from your hypothalamus to the adrenal medulla, causing it to produce those substances, epinephrine or adrenaline, and norepinephrine or noradrenaline. Now, the effects of these hormones compare to the stimulation of the sympathetic nervous system. So, if you think about what happened when the sympathetic nervous system was activated, well, look at the things that I've listed here. It's all the same kind of stuff. Increase in metabolism. Why do you need more metabolism? Well, if you're going to run away from a Tyrannosaurus, you need some blood sugar so you have energy. Increased heart rate, so your blood is pumping faster. Increased blood pressure, kind of because of that increased heart rate. The circulation is directed towards your heart and muscles because they need blood more. And then you'll see down here I noted that circulation to the extremities decreases. And there's lots of conversion of glycogen to glucose. Glycogen is the storage form for sugar and glucose is the usable form. So we're going to take all the sugar we got out of storage so we can use it for energy, and pupils dilate. So these effects are very similar to the effects of the sympathetic nervous system. So when you look at them, you'll say, yeah, okay, I knew these already. This is the sympathetic nervous system. Sympathetic nervous system effects are comparable to the short-term stress that your adrenal medulla will take care of. Okay? So that's short-term stress. Happens really quickly, but does not last a super long time. Now, the other side of the story is long-term stress. Long-term stress is the kind that takes a little while to get going, but then the effects last for a significant amount of time. The exact amount of time is not set in stone. This is the adrenal cortex's job. So that's the outer layer of the adrenal gland. Now, your adrenal cortex produces a few things. One category of hormones that it produces are glucocorticoids. So if I look at that word, gluco makes me think of glucose, sugar. Cortico, oh, well, it comes from the cortex. Oids, steroid hormones. So that's where the word is coming from. Specifically, we're going to talk about cortisol. So cortisol is a glucocorticoid. It's the most abundant one. It's the one that we're going to talk about. So glucocorticoid is the category. Cortisol is the example. Cortisol's job is to raise blood sugar. It does this by promoting the breakdown of proteins and fats into amino acids, which your body then converts into glucose. It also acts as an anti-inflammatory, so it reduces inflammation. And this might be the context in which you are familiar with cortisol. Maybe you've heard of athletes or people who have pain in a joint getting a cortisol or cortisone shot to reduce inflammation. And that's because it's an anti-inflammatory. It will reduce the inflammation response. And inflammation is something that can cause pain and reduced mobility, especially in joints. Now, this part down here at the bottom tells you the pathway for the control of cortisol. So, stress happens. What is the cause of stress? Well, there's many different types of stress. Remember, it could be psychological stress, physical stress. Stress eventually tells your hypothalamus it has to get this process in motion. Your hypothalamus will produce a releasing factor. Specifically, it's called CRH. The RH is releasing hormone. You don't have to know the names of the hypothalamus releasing factors, but lately on the diploma, they've been telling you the names of them, and so I find it useful. I should just tell you the name ahead of time. You don't have to memorize it. If we want you to know it, we'll tell you. But this way, it's a familiar thing. So this releasing hormone goes through the blood vessels that connect the hypothalamus to the anterior pituitary. the anterior pituitary will produce ACTH, and its name tells you exactly what it does. ACTH stands for adrenocorticotropic hormone. So, adrenocortical, the cortex of your adrenal gland. Tropic hormones are stimulating hormones, so it's telling you what it's doing. ACTH, because it's a hormone, will travel through the blood to the adrenal gland. Specifically, it's the adrenal cortex in this case. Adrenal gland will produce cortisol. Cortisol will have its effects that I listed here, and then there'll be feedback inhibition. Either the effect of cortisol will shut off the system, or just the presence of lots of cortisol will tell your brain, hey, we've got enough, stop producing more. Now that is one of the hormones that is coming from the adrenal cortex that you need to know about. Glucocorticoid called cortisol. Now, would anyone like to ask a question about this one? Okay. So there's another hormone that your adrenal cortex makes that will be important for stress. It's a mineralocorticoid. So if you look at the word, just like a glucocorticoid, the name is telling you what it is. Mineralo, so something affects minerals. Cort, or cortico, so cortex, and oid, steroid hormone. This hormone you may remember hearing about before. It's one that I know you normally learn in Bio30E with reference to the kidney. Aldosterone is the main mineralocorticoid that we would discuss. So, mineralocorticoid category, aldosterone hormone. This particular hormone, also produced by the adrenal cortex, stimulates sodium absorption by the kidneys. Now, this is important because water likes to go to places where the concentration is high. So if I think about osmosis and water movement, water follows sodium. So if aldosterone is making you absorb sodium out of the filtrate that's going to become urine and back into the body, water will also be removed from the filtrate, which will become urine, and go back into the bloodstream, so blood pressure will increase. Okay? So the mechanism is that it stimulates sodium absorption, but water follows sodium. Since blood is half water, reabsorbing water means that you have a greater volume in your blood vessel and it increases blood pressure. Now the feedback for this works in a very similar fashion to cortisol because it's controlled by the same pathway. Hypothalamus makes CRH. CRH stimulates the anterior pituitary to make ACTH. ACTH stimulates the adrenal cortex, and those two hormones are produced. Now, does anyone want to ask anything there? Okay. There are lots of other hormones in the world. We are just talking about the main ones that are involved. There's also lots of research into how people manage stress with adrenal insufficiency. And so I just want you to know this is not the entire story of everything. These are just some highlights of the story. Now here are some disorders that are associated with some of those hormones. The one on the top, Cushing's disease, is what this picture is referencing. Cushing's disease is caused by a hypersecretion of ACTH. So that's the anterior pituitary hormone that's stimulating the production of both cortisol and aldosterone. So if we have too much ACTH, we're going to have too much cortisol, too much aldosterone as well. So whatever effects they cause are going to be increased. Now, Cushing's disease tends to cause weight gain and fatty tissue deposits, especially around the abdomen and upper back, on the face, and between the shoulders, which is called a buffalo hump, which is not a super fun name for it, but these fatty deposits. It also tends to cause pink or purple stretch marks or streaks. And so you can see there's a few marks on the person's skin there. It tends to cause thin, fragile skin that bruises easily, slow healing of cuts, insect bites and infections, and acne. And if you think about what cortisol is supposed to do, cortisol, one of its jobs is anti-inflammatory. And so if I have too much cortisol, I'm suppressing the immune system response too much, which could explain this slow healing surface, or this slow healing thing here. If I think about the sugar portion of things, that can help explain this fatty tissue deposit and weight, because now we have way too much blood sugar circulating around in a person, can't possibly use all of that. Now, Cushing's disease is hypersecretion of ACTH. The kind of flip side of that is Addison's disease. In Addison's disease, you have an insufficient amount of those two corticosteroid hormones, so cortisol and aldosterone. The symptoms are hypoglycemia. That means low blood sugar. And I'll use the word hypoglycemia again tomorrow when we talk about blood sugar. NAK, so sodium-potassium imbalance. You might say, hey, we just talked about sodium and potassium. Yeah, you did. Nervous system. We have an imbalance of sodium and potassium. That can cause huge impacts on your nervous system. Rapid weight loss, general weakness, and low blood pressure. And that's very specifically in response to the lack of aldosterone, because that's the thing that we just saw was contributing to water reabsorption. Now, the fact that JFK had this is just for interest. No one's ever going to test you on that. But those are some examples of disorders that are related to stress. Now, this last thing here is just a summary of all the things that I already said today. But I often find pictures help me more than words, especially when I'm trying to remember a whole bunch of things or a long pathway. I like this picture because it shows me both responses to stress in one beautiful diagram. You can see up here, stress is affecting the hypothalamus. That's sort of the beginning of both pathways. On the left, I see a neuron going all the way to the adrenal medulla. I see epinephrine and norepinephrine being produced. And I see some short-term stress response effects. Glycogen converting to glucose, blood pressure increasing, breathing increasing, metabolic rate increasing, and blood flow patterns change. So remember I said less to the extremities, more to heart and muscles. On the right, same thing begins the pathway. Stress affects the hypothalamus. But this time, I see the releasing hormone going to the anterior pituitary. I see ACTH going through blood to the adrenal cortex. I see mineralo and glucocorticoids coming out. Now, I could just put aldosterone and cortisol there, because those are the ones that you need to know about. And then you've got the two sets of responses. The ones aldosterone causes on the left, and the ones cortisol causes on the right. If I was going to study how does my endocrine and nervous system respond to stress, I would study this picture, because it summarizes all of the things that we said, but in one beautiful little picture. Now, the last thing that I want to mention here is MSH. If you remember from your anterior pituitary lesson, the acronym was flat pig. So I thought of delicious bacon. And this is the M. This is the MSH and ACTH share the same precursor molecule, which is why I'm talking about it here. MSH is released from the anterior pituitary, and its release is increased by exposure to UV light. MSH stands for melanocyte stimulating hormone. So your melanocytes are in your skin. They make melanin, it's pigment. And so when you're exposed to UV light, your skin makes more pigment. That's why you get a tan when you're exposed to UV light, because of this pathway. And so even though this really isn't the same as stress, because it's got the same precursor molecule, like I make them out of the same thing, that's why I thought it made sense to put it here.